Hi there, my name is Jennifer Trammell and I'm going to be your chemistry instructor for this semester. I decided to pre-record the videos this time for the semester so that everybody could watch them at their leisure. You can see it's Christmas time here. And so you'll see, different things in the background at my house, but I'm hoping that that will help a little bit. What I'm going to do during this lecture is I'm going to do the first part of chapter 1. Now, don't be worried because I am going to have some live Zoom sessions. So if you want to be able to ask questions real time and work with me and work problems, that will still happen. This is just to supplement the slides. So notice that I said supplement the slides. What I really, really want you still to be doing is to be opening up those PowerPoint slides and those annotations files and taking notes on those. This is not meant to completely replace the stuff that we would do on a whiteboard in class. So I won't be going over a lot of definitions. I'll be doing some, but I won't be writing full definitions on the whiteboard because I am assuming that you are reading them. So don't watch these videos and think that you're getting everything that you're going to need. You're still going to need those. Okay, so without further ado, I'm going to go ahead and begin. Whenever I pause, it's because I'm doing things like selecting a whiteboard. Here we go. All right, so now what you're doing is you're seeing my whiteboard, and we're going to pretend like this is a whiteboard in class for real. Okay, and we're looking at chapter 1. And this is the chapter 1, part 1 video for week 1. That's handy. It's the only time during the semester that it'll work out quite like that. Okay, and what I'm going to focus now on is basically the math. I mean, that's primarily what I'm going to do during these videos. And so the first thing that we are going to look at, again, don't forget to read the slides because I'm skipping ahead. The first thing that this is going to look at is the metric system. Okay, so scientists use the metric system. They don't use the English system at all, or the standard system, And so we're not going to use things like inches, and we're not going to use things like miles, and we're not going to use things like Fahrenheit. However, unfortunately, because the US won't switch, you have to learn how to convert between the two systems. So we're going to be learning how to use the metric system, and we're going to be learning how to use how to convert between the metric system and the kind of the standard system that people in the USA are used to using, unfortunately. I have a pet peeve about that. I think that we should switch like the rest of the world. I'm just kind of going through some of this. Okay, but today what we're going to do is we're going to focus on the metric system. Next week we'll focus on going between systems. So that's kind of an important thing. One of the things that you're going to have to know for tests on your own is how to convert between units in the metric system. Okay, so I'm actually going to write the words. You need to know the conversion factors for this. Okay, so there's two main ways that we can go about that. One is with a large chart that covers almost everything, and one is with a few primary important values that we're going to use constantly throughout the semester. So I would write these down on a piece of paper and keep them handy every week while you're doing computations. And those really important ones are that there are 100 centimeters in 1 meter. Okay. Now, the way the metric system works is that you could also say that there are 100 centigrams in 1 gram. The number goes with the prefix. Okay, it doesn't matter what your base unit is. Meters, grams, those are base units, and it doesn't matter what those are. The prefix is all that really matters there. Okay. The next one is that there are 1,000 milligrams in 1 gram. And I'm not going to show different base units for this because that's something that we can work through. The next one that you're going to need frequently is that there are 1,000 meters in 1 kilometer. Now, these actually are in the slides, but I really want to focus on you guys making sure that you know these. These are the core ones that you will use this semester. Then there's 1 times 10 to the 6th microliters in 1 liter. Okay. And 1 times 10 to the 6th is the same as saying 1 million microliters in 1 liter. Okay. All right. So now, the last one that I want to look at here is that there are 1 times 10 to the 9th nanometers in 1 meter. And if you're saying, hey, nanometers, I've never heard of those before. Nanometers is the unit that we use to measure light waves. And so we'll learn the conversion now, and then we'll review it in chapter 7, and you'll see quite a bit of it there. Okay, and again, just as a review for scientific notation, that's the same as saying 1 billion nanometers in 1 meter. Okay, all right, so those are kind of our primary ones that we're going to be working with there. Okay, so let's take a look at how we would use these. Okay, let's say that we have, for example, 123 kilometers. And we want to know how many meters is that? Okay, well, if I use my conversion factors, then I know that there are 1,000 meters in 1 kilometer. So what I can do is I start with my known 123 kilometers, and you can put that over 1 if you need to remember that. That's the way we're working with it. Okay, and now we're going to use the conversion factor like a ratio. So I said that there were 1,000 meters per kilometer. So what I'm going to do is see how I have the kilometers on top, and now I need to put kilometers on the bottom so that they'll cancel out, and meters on the top, and then I remember my conversion and I fill it in. And then I like to check my units. Yep, that's the correct conversion factor, and I have kilometers on the top and kilometers on the bottom, so they'll cancel. Okay, and then what I do is I do my math. That's 123 times 1,000, or 123,000 meters. Now, if I want to, I can also show that like this, and sometimes it makes sense. 1.23 times 10 to the 5th meters. Great. Well, let's say though that I want to go farther. Let's say that I want to go with my 123 kilometers, and I want to know how many millimeters that is. Well, now I don't have one that goes directly from kilometers to millimeters. Okay, so I'm going to use 2. And I can say, well, I have 123 kilometers, and I have a conversion factor that will go from kilometers to meters, and that's what's up above. And I have a conversion factor that goes from meters to millimeters. And see how I've also set up my meters to cancel? And that conversion factor is that there are 1,000 millimeters in 1 meter. So always check your conversion factor and make sure that that's going in there correctly. And again, here we are, we're canceling our kilometers top to bottom. And then we're going to cancel next our meters top to bottom, and we're left with millimeters. So now what I do is I say I have 123 times 1,000 times 1,000. And here I have this, 123 million millimeters. Okay, well now this is getting silly, okay? So what we're gonna do is we're going to change that, again, to scientific notation, 1.23 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 to the 8th millimeters. Okay. Now, let's just use this as a moment to review where this came from. 1, 2, 3, 4, 5, and that's where that 5 came from. And 1, 2, 3, 4, 5, 6, 7, 8, and that's where that 8 came from. Okay. So that's one way of doing this. All right, now let's take a look at another one. Okay. And let's go the other way. Let's take a common one that you will see in this chapter, but also in chapter 7, okay? And let's say that we're working with light, and our light has a wavelength of 609 nanometers. Okay, that's within the visible light spectrum, but we can't do our calculations in nanometers for this kind of a problem. We're going to need it in meters. Now we set it up the same way that we did before. 609 nanometers times, okay, now remember our conversion factor, nanometers to meters, and again, because my nanometers are on the top here, I need nanometers on the bottom here. It's 1 times 10 to the 9th nanometers per 1 meter. Okay, so now what I really want you to do is pull out a calculator. Whatever calculator you intend to use for the class. I would muchly prefer if you didn't use your phone, mainly because I don't think the phone calculators work as well as dedicated calculators do. And then of course, if you're taking this class with me in person, you will not be able to use your calculator on your phone for the test. Becoming really familiar with your calculator is incredibly important. Okay, and they all work a little bit in a different way. Every calculator is going to do scientific notation differently. So you do not want to type in a 1 and then a times and then a 10 and then a caret and then a 9. Sometimes that will get you the right answer. Sometimes it will not. And it primarily will not when you have something like this in the denominator. And interestingly enough, sometimes it'll work and sometimes it won't. It's very finicky. Okay, so you need to look at your calculator. On this calculator, I actually have an EE button. So I would put this in on my calculator like this: 1 EE 9. Okay, and this is how I'll put scientific notation in. Some other options that I've seen on calculators is 1, and then maybe you have an EXP button, and then 9. Sometimes on graphing calculators, what you need to do is 1, and then it's second comma, which is your EE function, and then a 9. And on very rare calculators, I have seen 1 with a times 10 to the X button, and then a 9. Okay, so these are the 4 most common ways that I have seen for students to put scientific notation into their calculators. Okay, I'm going to change these into ones just so that you can tell the difference between that 1 and the comma. Okay, so again, not like this, like one of these. If you can't figure it out, then please contact me and I'd be more than happy to help you figure it out. The best way is to take a close-up of a picture of your calculator, okay, and email it to me, and I'll be able to tell you exactly which keystrokes to use. Okay, now when we do this, however, okay, so I type in my 609 divided by 1 EE9 equals, and now my calculator does this really annoying thing where it gives me the answer. It's kind of hard to see. It gives me the answer like this, and I don't want it like that. So if your calculator is doing that, one of the things that you need to do is you need to make sure that your calculator is going to give you the answer in scientific notation. Now, this calculator has a toggle button that will toggle between scientific notation and standard notation. If yours doesn't, you might have to go in and change it in the mode. And again, if you're not sure how to do that, that is almost better actually for me to help you with via Zoom. So let me know. Sometimes when your calculator gives you that long string of numbers, it will only give you one significant figure at the end. If you need 3 significant figures and you give me 1 and you overround that much because you didn't toggle into scientific notation, it will be wrong. So make sure that you're not taking that 1 digit at the end. Okay, and more on that as we go. Okay, so here, this answer becomes 6.09 times 10 to the negative 7th meters. I muchly actually prefer this to be in scientific notation. However, in standard notation, let's see what that would be. We have this negative 7 here, and that means that our decimal point is going to go the other direction. This counts as our first place, okay? So we would count 1, 2, 3, 4, 5, 6, and then the 7th place is the 6. 09. And that's how we would do that particular conversion. Okay, so now let me see if I can. Okay, now what we're going to do is I'm going to show you a large thing that's in your slides. So give me just a minute to find it. I'm trying to see if I can cut and paste, and I thought it would be simple, and now it appears not to be. Okay. Instead, I'm going to stop my share, and we're going to just go right to the slides. Okay, so we're looking at this slide now, and let me see if I can. Okay, it might not be real clear. I'm trying to. There we go. Okay, now you can see this a little bit larger. Okay, so let's take a look at this table 1.2. This is in your slides. It's also in your textbook if you've opted for a hard copy of a textbook. And let's take a look at how to use that. Okay, so here you can see these. And what this is right here is this is your base unit. It might be grams, it might be meters, it might be liters, it might be seconds. That'll be more common in Chem 2 when you take kinetics. Okay, those are your base units. So how are we going to use this? Well, you can see these here. And what this would mean is, let's say now that we're going to go from one to another. And let's say that we want to go from decigrams to kilograms. Okay, well, there's different ways of doing this, but one method for doing that is, let's say that we're going to say that we have 55 decigrams and we want to go to kilograms. Okay, this is the method that I prefer. So what you see here, you see this 0.1 with the deci. Okay, that means all of these refer to the base unit. So that means that you would take that and you would say then 0.1 grams per 1 decigrams. Okay. And now we've gotten rid of our decigrams and we have to go to kilograms. And there's the 1,000 that goes with kilo. And so that would look like this: 1,000 grams per 1 kilogram. I'm not sure what that extra line is for, and I don't have a lot of annotation tools on this page, so just ignore it. Okay, well now what we've got is we have, and I'm just walking you through this, 55 times 0.1 times 1,000. Okay, and that will give you, oh, did you see what I did? That was terrible. Let's look at that again. Okay, that's 55 decigrams times, okay, this isn't working at all. Stop share. Let's come back to the whiteboard. Okay, so we had, remember what those were. Okay, let's actually fill that in a little bit from what we had before. Here we had kilo, and it tells us K, and then it tells us 1,000, okay, and then it tells us 10 to the third. Let me actually fill this in a little bit here. Then we have hecto, and that gives us an H, and 100, and 10 to the 2. Okay. And then we have deca, DA, and 10, and 10 to the 1. So this is standard notation. And this is scientific, sometimes called exponential notation. And then we have our base. And then we have deci, and then centi, and milli, okay, and this is 0.1, 0.01, 0.001, and this will be 10 to the negative 1, 10 to the negative 2, 10 to the negative 3. That's what that chart in your slides looks like. Okay, so let's take a look back at that and see, okay, well, what would some of that look like? Okay, so we have that 55 decigrams, we said, okay? And according to this here, we see that 0.1, and we see 10 to the negative 1. So what does that mean? Okay, well, that means that you can either put in 0.1 or you could put in 1 times 10 to the negative 1. So you need to kind of change all these. 1 times 10 to the 1, 1 times 10 to the 2, 1 times 10 to the 3, 1 times 10 to the negative 2, okay, and so on and so forth for that whole chart. Okay, and so that's, sorry, it's hard to talk and write at the same time. Okay, so we need our decigrams here and our grams on the top. 1 decigram is 0.1 grams because these numbers always refer to our base unit. And now we're going from grams to kilograms, we had said, okay? And that was what I had messed up on the other slide, sorry. So we know that there's 1,000 grams in a kilogram, and that's from this. And remember, these always refer to that, okay? So now we say 55 times 0.1. Now, I always hit equals in between. Some calculators don't require that, and some do actually, especially if you've got a lot of things that you're dividing by. So you're just gonna have to play with it and make sure that your calculator gives you the same answer that mine gives me. And then we're gonna divide that by 1,000, okay? And that will give us I'm running out of room. 0.0055 kilograms. All right. Let's practice going farther. Okay. We'll go from the top now to the bottom. Now, what I'm going to here. Okay, so let's do a really big one. Okay, if I look at my chart here, which is printed extremely small, I will see giga. Now let's go really big. Let's go to tera. And it says tera, and the unit for tera is a capital T. Don't mix up your capitals and your lower cases for this. And what they tell us here, well, there's way too many zeros there. I don't want to count them. So we're going to go, it says 10 to the 12, which I know means 1 times 10 to the 12. And we'll go with meters just for the fun of it. Meters in 1 terameter. It's always based to there. Now, if we go way down to the bottom, let's look at femto. Femto has a small f, and it is 10 to the negative 15th, which means there are 1 times 10 to the negative 15th meters in 1 femtometer. Okay, so let's say that we have 13 terameters, and we want to know how many femtometers they are. This is one way to do this. I know that there are multiple ways to do this. If you have a different method, please just show me your work, okay? It's absolutely forbidden for you to plug this into Google and do it that way. You have to show your work. You have to show what you're doing so that I know that you're not using Google. All right, so we have 13 terameters. Now I use the conversion factors that are up here, and I'm going from terameters to meters. So in 1 terameter, there are 1 times 10 to the 12th meters. Okay, and now I need to go from meters to femtometers. So I have meters to femtometers. And there are 1 times 10 to the negative 15th meters in 1 femtometer. Okay, so now what we have is, now let's practice again putting this into our calculator. So we have 13 times 1 E12, okay, and now I'm going to divide that by 1 15, and I'm going to put in my negative. So my calculator does things in really weird order, okay? You're going to have to figure out how to do things with your calculator. I strongly recommend that you pull out your calculator and you do this problem now so that you don't have a calculator malfunction on the test. And what I get with this is 1.3 times 10 to the negative 28 femtometers. And that would be my final answer. Okay, so that's how you're going to do these unit conversions. The next thing that I want to talk about today, for that first part of chapter 1, that might be a little bit challenging for some folks, is significant figures. Interestingly enough, students detest significant figures. They just do. And it takes a really long time sometimes to be comfortable with the concept. And the reason for that is because what significant figures do is they tell you how confident you are in your final answer. So every time we use a number in science, we have some level of confidence in how accurate the number actually is. And remember that accuracy is how close we are to the agreed upon value. I'm not going to talk about precision and accuracy here. There's a lot of that in the slides, and there's a lot of it in the annotations file, and there's some linked videos. So watch those and look at those. That's more of a concept thing than a math thing. Okay, so what the significant figures are doing is they're saying, well, we're this confident with this measurement, and we're this confident with this other measurement. So when we multiply or divide or add them, how confident we are depends on a mixture of those confidence levels. basically down to the least confident. So your calculator can give you 10 digits, but that doesn't mean that we're confident to that. And I've heard people say, well, I want to use all the digits because that's more accurate. Well, that's a misinterpretation of the idea of accuracy. We cannot report numbers that we aren't sure are accurate. Just because the calculator gives them to us doesn't mean that they're accurate. It just means it's math. So this is where we're really different than we would be in math. So let's take a look at some of that. Let's say that, so first of all, let's take a look at our significant figures rules. The first rule is that, let me make sure that I'm going to get them all. Okay. All non-zero integers count. Okay, so what that means is that if I have 123 or 4,972 or 1, 2, 3, 4, 5, 6, 7, 8, 9, 3, because I need another one there. All of these digits count, okay? So this one will have 1, 2, 3, 3 significant figures. This one will have 1, 2, 3, 4, 4 significant figures. This one will have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 significant figures. Okay, let me toss one more in there. Let's say that we have 536.728. This one will have 1, 2, 3, 4, 5, 6, 6 significant figures. That's the easy part. Okay, so if that's the easy part, what's the hard part? The hard part are zeros. Why are zeros hard? Because we have 3 different rules for them. Okay, case A. Okay, case A are leading zeros. And leading zeros are zeros out front. Let's say that we have 0.00253 or 0.000000721. These are what we would call leading zeros. And in this case, there are 1, 2, 3 significant figures because leading zeros never count. This one has 1, 2, 3. 3 significant figures because leading zeros never count. And part of the reason for that is because we can put these into scientific notation. This becomes 2.53 times 10 to the negative third. And this becomes 7.21 times 10 to the negative 1, 2, 3, 4, 5, 6, 7. 10 to the negative 7th. In each of these cases, we still have 3 significant figures. And that's one of the reasons that our leading zeros never count. Our second possibility are what they call captive zeros. Now, captive zeros are zeros that are between 2 non-zero digits. For example, 506 or 4001. Or maybe 130.706. All right. In all of these cases, the zeros count because they're bracketed by non-zero digits. 4, 5, 6. Okay. So we have 3 significant figures here, and 4 significant figures here, and 6 significant figures here. I've run out of room. I'm going to put C on the next page, so to speak. Okay. So C has, the C case are what we call trailing zeros. And trailing zeros happen at the end. So now you have 3 different cases for trailing zeros. Okay. Case number 1, no decimal point. If we have no decimal point, 4,700 then we have two significant figures. Because with no decimal point, the zeros do not count. Now let's say that we have a weird intermediate one where it ends with our decimal point. 4,700 point. You'd never see this in math, but it's okay here, okay? And in this case, we have all four will count because there's a decimal point. Now let's say that there's a decimal point anywhere. Okay, then they all count too. So let's say that we have 4700.00. We are very confident about this number, and it has 6 significant figures. Okay, and what would these look like in scientific notation? This one would be 4.7 times 10 to the third. This one would be 4.700 times 10 to the third. And this one would be 4.70000 times 10 to the third. And then we keep 2 significant figures, 4 significant figures, and 6 significant figures. Okay, this is tricky. Okay, so don't worry if it might take more than one go. All right, now let's use these significant figures. Okay, first of all, let's figure out what they would be for multiplying and dividing. For multiplying and dividing, our answer will have the least number sign, not hashtag, of significant figures. Okay, so let's say that we have 4726 times 3.1. I put this into my calculator, 4726 times 3.1. And the answer that I have here is 1465.6. However, this is where significant figures are so important. I'm only 2 digits confident. I'm not super confident with that second number. Therefore, in a way, it would be a lie for me to report this number, because in the scientific world, what it says is I'm super confident. Look at all my significant figures. And that's not okay. We need to tell people how confident we are. We can only have 2 significant figures here. So we need to cut it off here. Please remember your rounding rules, and this is very important. This number becomes 1,500. 1,500 is our final answer for this value. Okay, the 6 rounds that up because it's 5 or greater. Okay, now let's take a look, and there's a lot of this in the annotations as well as in the slides themselves. Now let's take a look at adding and subtracting. And in this case, our answer will have the least number of decimal places. And that's because we're comparing magnitudes in this case. So let's take a look at this. Let's say that we have 4,726 plus 3.1. Okay, well now what we need to do is we need to line them up. So I would say 4,726 plus 3.1. And I add them up. Okay, now with this, this is the magnitude that I am confident in. So now what I need to do is I need to round this for significant figures. Now a 1 rounds down And so my final answer here is 4,729. Okay. There's one final piece of significant figures that I want to discuss with you, and those are exact numbers. What's an exact number? An exact number is something that contains an infinite number of significant figures. Because we are exactly or perfectly confident. Some examples of numbers are metric system conversions. 1,000 meters in a kilometer. This is exact. Let's say that I have 1 times 10 to the negative 9 nanometers in 1 meter. This is exact. Let's say that I have, now this is the only place where the value is exact, 2.54 centimeters per inch. This is also exact. For other values, the numbers are not exact. For other conversions between systems, let me see if I can find one that I have available. Okay, let's say that I am using the fact that there are 2.2046 pounds in 1 kilogram. Now, in this case, this number is not an exact number. This 2.54 is exact because it's defined as exact in the same way that the other ones are. But this is not. This is sort of an approximated value. And so in this case, we would have 5 significant figures. The last place that we have exact numbers is numbers that are counted, not approximated. So let's say that I count and I have 20 students. Because I've counted this value, it is exact. And whenever we have an exact number, we ignore that for significant figures. We wouldn't say, oh, look, I can only have 1 significant figure in the end because it's exact. That wraps up the end of the first part of chapter 1. Hopefully, I will see you all during recitation. Bye.